Well, hello there, it's me again. Hey, I want you to think just a little bit about projectiles. I hope you had a chance to check out the videos from the previous post. If you haven't, it would make a lot of sense for you to look at those first and then jump in on this conversation. Hey, but what I want you to recognize is a projectile is any object that's moving through the air affected only by the earth. Now, you saw my videos where I was outside and I was tossing a couple of balls in the air. And I want to recognize that those are always projectiles after they leave my hand. As soon as something is only being acted on by the earth, it's a projectile. Now, if it's getting pulled on by other forces or by your hand still, it's not a projectile. So, like the example here talks about airplanes, yeah, those aren't projectiles because there's other interactions going on. But projectiles are that straightforward. So let's look at a couple ideas together. Some vocabulary words that I bet you have seen. This word called trajectory, that's just the name of the path that a projectile follows. And of course, it has a mathematical shape called a parabola, or as I like to say, a parabola. And you've probably seen the word range as well, because we thought about that in the lab the other day, which is simply a measure of how far something travels sideways. And as you've now seen from your work in the lab, that does depend on the speed, that is the launch speed that you launch something at, and it depends on the angle, that is what angle you launch something at. So today we're going to dig in just a little further to two-dimensional motion, and I want you to think with me about how both horizontal and vertical motion can be tracked in a projectile. Now we think about those two things, but the neat thing is we can think about them separately. Again, you noticed when I launched one ball sideways, it began to fall and it hit the ground. The other ball fell straight down and hit the ground. And the neatest part about that is those two hit the ground at the same time. And the point is that regardless of whether something is moving sideways or not, the vertical motion is still the same. So when we see two-dimensional motion, the neat thing about it is that there is what's called independence of horizontal and vertical motion. That is, something moving sideways doesn't affect the way it moves up and down. So again, we're going to think about that in the context of projectiles. We talked about range. Here's a cool thing you might have noticed about symmetry. 45 degrees, you probably saw in your experimentation, gives you the biggest range. Things go the farthest at 45 degrees. Hey, if you subtract 15 from 45, well, you get 30 degrees. But if you add 15 to 45, you get 60 degrees. And the cool thing is, assuming there's not much air resistance to worry about, those two those two angles give you the same range. Both of them less than 45, but they're the same. And likewise, any angle away from 45 to either side of 45 is going to give the same result. If we go all the way back to 10 degrees and all the way up to 80 degrees, we're going to have the same result. Kind of a neat idea to think about, that symmetry. That pops up a lot of places. So again, that's an idea that we thought about. And it definitely depends on how long an object is in the air. Let's get down and talk about the details. This picture is a really useful picture to think about. Now, it's a little bit hard to see, so let me bring it up a little bit. What I want you to notice is the shape of these arrows. As an object travels through the air, like we've been talking about, the horizontal speed doesn't change. Look at this. As it goes through the air, it keeps going the same speed sideways all the time. Yet as it goes through the air vertically, initially it's not going down at all, but immediately it starts to drop, and as time goes on, it goes faster and faster and faster in the downward direction. So you notice right away the velocity is straight sideways, but over here it's a combination of sideways and down, and as the object goes farther along its path, its trajectory, that angle keeps changing and getting further. I don't like my picture for this first one. I don't think my picture is very good. Let's make that better. So the neat thing again is that with two-dimensional motion, we start to see how we can pick it apart. And I want you to notice that the horizontal velocity, it stays constant because there is no force once the projectile is moving by itself. When it's a projectile, there's no force acting on it sideways. There is a force acting on it vertically, and that is the gravity pulling, the Earth's pulling on it. So vertically, we don't see a constant velocity. We see acceleration. Of course, that's just a fancy word for speeding up, right? So we have things sideways that move steady, 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 but then vertically they go faster and faster and faster. Now, these next two slides are going to pick that apart just a little bit. So let's look at this together. Here's a picture that represents that idea pretty nicely. This shows us that as something goes through the air horizontally, its speed remains the same. Notice that's what we just saw in this picture. But as it goes through the air vertically, the speed increases. And there's some mathematics we can use here. This particular equation is the least needed of the three that we're going to have today. But this tool right here simply says that the speed something has in the vertical direction is equal to the product of g, or if it helps you to think of that as acceleration due to gravity, it's the same thing, 9.8 meters per second squared, times the time that it's in the air. That is, the speed is going to keep increasing the same amount every second. Now, again, we're not going to have to worry about that equation so much. We're going to really focus on distances, but it's kind of neat to see. But let's go think about two distance tools. Here's two tools that I want you to capture in your physics notes or somewhere on paper so you can use them on problems today. We've just talked about the idea that horizontal velocity is constant. So the distance something travels horizontally is just the same tool we've been using all along. It's just velocity times time. That's all there is to it. We take the horizontal velocity, we multiply by the time, and we've got the distance. But if we're going to deal with vertical distance, it's a little bit different. You notice the vertical distance depends on the time squared. That has to do with the idea that things go farther and farther and farther as they travel. So if you drop something from rest vertically, it's going to get faster and faster. So these vertical arrows that represent the speed are going to get bigger and bigger. But horizontally, they're all going to stay the same. So again, these two mathematical tools, these relationships, are super useful to solve some problems. Let's look at one example, and then I'm going to ask you to try some together today. The example I want to have you look at is right here. It looks a little bit wordy, so let's not get too worried about how many words there are here. But let's take a look. So we have a driver driving off a cliff at 20 meters per second. 20 meters per second off a cliff. Okay, bad idea. The car lands in a lake below 2 seconds later. Find the horizontal distance the car travels and the height of the cliff. So we're given a couple of things. 20 meters per second, that is a velocity in the x direction because it's only sideways, right? 2 seconds later, well, that's a time. And then let's look at what we're trying to find in this problem. Find the horizontal distance, that's one of the things we're trying to find, and the height of the cliff, that's the other. Well, horizontal distance is what we call dx in those equations we just played with, and height is dy. It's a distance in the vertical direction. So all you see from here is these very same two tools we had a minute ago. Here's dx, that is the distance it goes sideways. It's just speed times time. And here's dy, that the distance it goes vertically depends on the time squared. So to solve this problem, all you're going to do is plug and chug, right? Vx is 20. This 20 meters per second goes in here for Vx. The t is our 2 seconds. Hey, 20 times 2, 40 meters. Check. Well, the t also goes in the vertical equation, and that's the only thing we need in there. So the 2 seconds also goes in here. 2 squared, let's see, that's 4. That's 4. 4 times 4.9. Vertical distance is 19.6. So while it seems kind of complicated, recognize there's only two things we're doing here. We're using the x distance equation and the y distance equation. Let me back up one slide. These two tools are the ones you need. Distance horizontal, velocity times time. Distance vertical, 4.9 t squared. Let's take a quick look at the problems that we're going to go after today. They look like this.